Welcome back. This is the third lecture in our unit of stereoisomerism. In this video, we will tie up loose ends, taking a closer look at stereoisomeric relationships, namely enantiomers, diastereomers, and meso compounds. And then we will end the lesson with optical activity. Alright, so let's first start looking at stereoisomeric relationships. And to help us out, we will draw a map to help us see the relationships. At the top of this map, we have what are known as isomers, so molecules that have something in common with each other. They are broadly called isomers. Now, when these molecules share the same components in terms of atoms, they are made up of the same types and same numbers of atoms. They are called constitutional isomers. And what we really focus in this chapter is beyond constitutional isomers. Not only are molecules sharing the same atoms in a number of atoms, but they also share the order of connectivity of these atoms. However, what differentiates them then is that the 3D orientation of the various atoms. And these molecules are known as stereoisomers. Alright, so far nothing is new to us. We have already seen these concepts before. Now, let's take a deeper dive into this category of stereoisomers. The bulk of the lecture so far, we focus on a type of stereoisomers known as enantiomers. And so remember, enantiomers are a chiral molecule that has a mirror image that is non-superimposable. However, if you are a stereoisomer, but you are not the mirror image to your stereoisomer, then there's a different name for your relationship. You are known as diastereomers. So this is a new term, so let's go ahead and unpack this and see the difference between enantiomers and diastereomers. To help us illustrate this point, let's look at an example. Okay, so here we go. We have this molecule. It is a chiral molecule. Let's go ahead and compare it to this second molecule that I've drawn here. Can you recognize their relationship? If you go ahead and flip this molecule around like a pancake, you should see that it is a mirror image of that first molecule, but it is non-superimposable. So what do we say? We say that they are enantiomers of each other. All right. Let's draw some other molecules that are also stereoisomers of these two molecules. So everything's the same in this molecule except for the methyl group. I'm going to draw it down. I'm going to go ahead and number our molecules so we can speak of them much more easily. So the third molecule that I drew, what is its relationship to, let's say, molecule number 1? Notice that they are not mirror images of each other, but indeed they are stereoisomers, right? So based on that relationship, they are called diastereomers. What about molecule number 2 with respect to molecule number 3? Again, they have the same constituents, they have the same connectivity, but there's a difference in 3D orientation at the chiral centers. So they are indeed stereoisomers. However, they are not mirror images of each other. So again, they are diastereomers of each other. Great. Let's draw one more stereoisomer. This time I'm going to have the hydroxyl group as down and the methyl group as up. Right? So that's all the combinations that we can come up with. And this molecule, we'll call it number 4. All right, so go ahead and convince yourself again that this fourth molecule is indeed a stereoisomer. And go ahead and ask yourself, what is its relationship to molecule number 1 and to molecule number 2? They are stereoisomers, but they are not mirror images, right? So therefore, they are diastereomers. So this molecule with this molecule is a diastereomer. And this molecule with this molecule is diastereomers. And then lastly, what is the relationship between molecule number 3 and molecule number 4? Were you able to convince yourself that if you did a pancake flip of one of these molecules that they will be mirror images of each other? Great. So they are mirror images of each other, but they are non-superimposable stereoisomers. So they are enantiomers. So there we have it. That's the entire map of the relationships of these stereoisomers. And hopefully that example illustrates to you the difference between enantiomers and diastereomers. Now let's take a deeper dive into this and let's see if there's some kind of patterns that emerge. So we said these molecules are chiral, so let's take a look at their chiral centers. Let's go ahead and see what is the configuration of these chiral centers. So in this one, we have the OH group as priority group number 1, the bottom group here as number 2, and the third group on the top as number 3. So that is indeed an R configuration. For the chiral group, for the second chiral center, this would be number 1 priority group, number 2, and number 3. So that is an S configuration. Let's go ahead and do this designation for the rest of the chiral centers. Over here, notice that if the OH group was going as a wedge up at us, it is an R. In this case, it is the opposite orientation. It is going away from us, right? So by definition, it must be an S. But of course, you can convince yourself of that by doing it the long way. The same thing goes for this chiral center. On the molecule number 1, it was a wedge and it was designated as an S. And this one is a dash, so it must be an R. It must be opposite of each other. Okay. Continue over here in molecule number 3. You have your OH going up, which was an R. We know that already. CH3 going down, in this case, was also an R. Molecule number 4, OH going down away from us, was an S. The methyl group going up at us with a wedge is an S in this case. All right, so there we have our RS configuration designated. What patterns you see emerges? Hopefully you see that to be an enantiomer, every single chirality center in your molecule is opposite to each other. Right, so that is a very good way to tell if two molecules are enantiomers of each other. To quickly designate the RS configuration and to see at every single chiral center there is a swap in R and S. Let's say there's 5 chiral centers and there's 4 of them that has swapped properly, but there's 1 chiral center that remains the same, then that doesn't qualify. And so therefore those 2 molecules would not be enantiomers. They would be diastereomers, right? Because if 2 molecules are stereoisomers but they're not enantiomers, then by definition they will be diastereomers. And so we see this in both of these pairs of enantiomers, right? In the first pair, in molecule 1, this position is swapped from R to S, and this position is swapped from S to R. In the second pair of enantiomers, they are both R's and they both become S's. And a little aside note here of the number of stereoisomers you can get. There's an actual math for this. It follows a formula. The number of stereoisomers is 2 raised to the nth power, where n is a number of stereocenters. So for example, if you're a molecule with only 1 stereocenter, that'd be 2 raised to the 1 power, which is 2, right? So you would just have you and your enantiomer. And in this case, we have 2 stereocenters, so it'd be 2 raised to the 2nd power, which is 4, which is why there are 4 stereoisomers. Now this rule breaks down a little bit when we come up with a molecule that is called a meso compound. So let's go ahead and take a look now at meso compounds. So remember we said that if we have 1 chiral center, your molecule will definitely be a chiral molecule. Now it turns out if you have 2 or any even number of chiral centers, your molecule can be chiral, but it doesn't have to be. So let's take a look at why and take a look at some examples. So we have here a molecule with 2 chiral centers. And if we drew this other molecule, its stereoisomer, we see that it is a mirror image, but it is non-superimposable, right? So we call that enantiomers. Now let's draw another set of molecules for comparison. This third molecule here, if we drew a similar mirror image, are these 2 molecules enantiomers of each other? And actually the answer is no. You can convince yourself of this. So if you were to rotate this molecule around, they can be superimposed upon each other. So therefore these 2 molecules are exactly identical molecules. How did this happen? Why is it in the first set we have enantiomers, but in the second set they are actually the same molecule? And it has to do with something called an internal plane of symmetry. When a molecule with an even number of chiral centers and an internal plane of symmetry, that molecule is achiral. So it is achiral, it is not chiral, so its mirror image therefore is itself. You can only have a mirror image that is enantiomer if you are indeed chiral, but if you're not chiral, then your mirror image is just yourself. Okay, and so what is this internal plane of symmetry? Simply put, if you were to draw a line through this molecule, then what you have on one side of the line is a perfect reflection of what you have on the other side of the line. Whenever you can draw that line is called an internal plane of symmetry. And so when you have this type of molecule where you do have chiral centers, your mirror image is yourself and not a different molecule and not your enantiomers, we have a special name for that type of compound. It is called a meso compound. So that molecule is the meso compound. And again, a meso compound, its mirror image is itself. Miso here, just like that Japanese soup, miso. All right, and to wrap up this conversation, as a review, what is the relationship between molecule 1 and 3 then? Good, they are diastereomers. What about 2 and 3? They are also diastereomers based on a definition we just learned. So that wraps up our conversation looking at the different relationships between stereoisomers. So how similar are enantiomers? We'll take a look here at an example of carbone. The molecule on the left here is R-carbone, and the molecule on the right is S-carbone. So because they are enantiomers, they obviously would have the same molecular weight. So that characteristic they will share. They will also share the same melting point, in this case at 25 degrees Celsius, and the same boiling point at 231 degrees Celsius. And that makes sense, right? Because those physical properties are based on intermolecular forces within the molecule. And just because there's a difference at the chiral center doesn't change the intermolecular force of these molecules. However, there are some differences between these two molecules, or else they would just be identical molecules, right? And it turns out our noses can tell these two molecules apart. The molecule on the left, R-carbone, smells like spearmint. It's like a minty sweetness. Whereas the molecule on the right, S-carbone, smells more spicy, like cumin or fennel. And the reason why we can smell them differently because they interact with our olfactory molecules differently. So there are chiral molecules in our noses that will respond differently to the different chirality of these two molecules. So in that example, we saw how R and S-carbone are distinct based on their biological properties. And this is a very important feature of enantiomers, especially when it comes to drug design. You want to make the enantiomer that has the desired therapeutic effect. Well, another distinction between enantiomers will help us determine which enantiomer we have, and that is called optical activity. And so you can tell the difference between these two molecules or any set of enantiomers based on their optical activity. And this difference is in the way the molecule interact with plain polarized light. So let's take a step back and take a look at light again. As you know, lights or photons travel in waves, electric and magnetic fields, and these waves are perpendicular in their planes. And so the orientation of this electric field, shown here in red, is called the polarization of the light wave. So when these waves travel in the same direction, they each have their own polarization, and they're all randomly oriented with respect to one another. So let me represent that with this light source with all different orientations of the electric fields, the polarization. And in particular, when we are taking a look at a device called a polarimeter, we are looking at the light of sodium and using its D line, which has a wavelength of 589 nanometers. With this light source, we can submit it through a filter, and this filter has a slit to it. And as this light is traveling through this filter, only one type of photons can go through, the photons that matches with that filter. So only one plane of light can go through. And so this light is called plain polarized light. And so this light was called unpolarized. And this kind of polarization is similar to the concept when your sunglasses is polarized. It only allows one type of light to go through. And so when we pass this light through a tube filled with our sample, known as the polarimeter tube, the substance, the molecules, will bend this plain polarized light either clockwise or counterclockwise. The more molecules this light hits, the more it will bend. And when it exits this tube of substance, on the other end, we can analyze how much it has bent. For example, this polarimeter tube and the substance in it bent this light at a 45 degrees angle. So it turns out enantiomers bend this light in opposite directions, but in equal amount. For example, if the R enantiomer bent this in the 45 degrees angle, then the S enantiomer will bend it at negative 45 degrees. And so this rotation at which the light is bent when it comes out of the sample is called the specific rotation, and is designated as alpha in a bracket. And remember we said that the more molecules this light hits, the more it will bend. So this specific rotation, we want to standardize it. And so in order to standardize it, we want to measure our sample at 1 grams per mil and in a path length of 1 decimeter. Now, as our samples in organic chemistry isn't that concentrated, in order to calculate the specific rotation from an observed rotation alpha, we just need to divide it by the concentration and by the path length. Again, the concentration would be in grams per mil and the length is in decimeters. If we divide it by this, we basically have made it standardized to unity. So we have here 2-bromobutane. On the left, we have the R enantiomer, and on the right, we have the S enantiomer. And we can measure its specific rotation. And it turns out this specific rotation will be dependent on the light that you shine onto it and the temperature that you have your sample as. So often this number is reported. So for example, if you see it written like this, that means it is recorded at a temperature of 20 degrees Celsius and with the light of the sodium D line. So in any case, in this example, our R enantiomer gave a reading of negative 23.1 degrees. So because of that, what do you think our S should read? It should be equal but opposite, right? So it's going to be positive 23.1 degrees. Another term I want to introduce here is that when that alpha reading is negative, we say it is turning the light in a left-handed manner. That is called levorotatory. We can sometimes call this L2-bromobutane. And when your sample turns the light in a right-handed manner, it is called dextrorotatory, signified by the letter D. So again, S2-bromobutane could also be called D2-bromobutane. Now, the L and the R does not have to go hand in hand. The D and an S does not always have to go hand in hand. Sometimes an L could be an R or an S, and so therefore the D could also be an R and S. So there's no direct correlation between these two labels. Okay, but do know that L will always be a negative specific rotation and D will always be a positive specific rotation. And one more distinction between these two systems is that the R and S, you can always determine by just drawing out the molecule, because that's just a system that we have come up with as a shorthand to name the compound. Whereas L and D is an intrinsic property of a molecule that must be measured. You can't determine it just by knowing the shape of the molecule or knowing the identity of the molecule. You would have to experimentally determine it. You have to measure it out for every single molecule. Now let's turn our attention to a concept called Enantiomeric Excess. So when a solution has one single enantiomer, it is said to be optically pure, or we can also say enantiomerically pure. Often, however, when we do a reaction, we do not get this purity. We will get a mixture. We'll get both of the enantiomers. Sometimes a 50-50 split, but most of the times one enantiomer will be more favorable, so it will be in higher concentration than the other. In any case, what we have then will be called a racemic mixture, As I said, this just means that it contains both enantiomers in the solution. Now, as we said before, it could be a 50-50 split. You have 50% of one enantiomer and 50% of the other enantiomer. And remember we said that they rotate light in opposite but equal direction. So if you have 50% of them, then one will rotate light in one direction, the other will rotate light in the opposite direction in the same degrees. So overall, that light will look like it has not been rotated at all. And this is very special when you have this instance, when you have a 50-50 split. And when that happens, since light was not rotated, we call that sample optically inactive. So when you have a 50-50 mixture of a sample that it is chiral, it would have the same inactivity as a sample that was not chiral at all to begin with. But beyond this 50-50 mixture, you will always have one that will dominate more than another. And that is what we call enantiomeric excess, when one enantiomer outweighs in concentration the other enantiomer. Let's say you have a 90% of one enantiomer, and we found out that that was a negative optical rotation versus a 10% of the other enantiomer. Then we would have 80% enantiomeric excess. And so how do we come up with this 80% number? Just imagine that if you have 10 that's rotating in the other way, then it will cancel out with 10% of the other molecule that rotates in the opposite direction. So what we have is an 80% excess of the enantiomer that is the majority. So we call that an 80% EE. Since we have an 80% EE of the enantiomers that rotate to the left, then your observed rotation will be a negative number instance. What about if it was in the opposite case? What if we had a 5 to 95% mixture? What would be its enantiomeric excess? Can you calculate that? Yes, it would be 90% enantiomeric excess. Again, if we had 5% rotating in the left direction, then it would cancel out with the 5% of the one rotating in the positive direction, leaving 90% in excess. Those are just simple illustrations, but there's actually a formula you can use to calculate percent EE. And that formula is that percent EE is equal to the observed rotation, absolute value, divided by the specific rotation of the pure enantiomer. Again, that is in absolute terms. Of course, this is a percentage, so you want to multiply that by 100%. So let's go ahead and do an example of this type of calculation. So the example problem here states that the specific rotation of S corvone is measured to be positive 61 degrees, right? And a mixture that contains both R and S enantiomers is measured to be negative 23 degrees. So the question then is, which is in excess and what is the percent EE? And what percentage of both enantiomers are in this mixture? Okay, so we can use this equation. So first off, which is in excess? Since we stated that the S enantiomer has a positive number, but the overall reading of this mixture is negative. So that tells us that the opposite enantiomer, the R enantiomer, is dominant. It is the one in excess. Okay, the next question is, what is the percent EE? So how much in excess is the R? So we're going to use the equation that we just introduced here. And in this equation, we have on the top here is the observed rotation, which is negative 23. But again, it's in absolute values, so we're just going to put in 23. And then on the denominator here, the optical rotation of the pure enantiomer. And the pure enantiomer's optical rotation turns out to be positive 61, but again, we're just using in absolute terms, right? And just multiplied by 100. So when we do that, we get that the percent EE turns out to be 38%. So let's break that down a bit. What does that mean if it's in 38%? Okay, so first off, that means you have 38% of it is definitely going to be an R species. And the leftover 62% is an equal mixture of R and S, right? So that means when you split that in equal parts, you then would have 31% S and 31% R. We know we have a 31% S, and the combination of 38% and 31% will give us 69% being the R configuration. So another angle you can take a look at this in understanding percent EE is that if you have here a 38% enantiomeric excess, that means only 38% of that sample can rotate the light in one direction. Remember that the other 62% cancel each other completely, making the sample optically inactive. So only 38% of the sample can make this sample optically active. And since we said the optical activity is concentration dependent, you can imagine that this sample is only 38% effective in rotating the light. So if we know that there is only 38% of the R, and the R can rotate this sample by negative 61 degrees, then 38% of that turns out to be negative 23 degrees. So that's what we get as the observed rotation when there is only 38% enantiomeric excess, right? And so from a practical perspective of organic chemistry labs, when you are performing a reaction, you want this EE number to be as high as possible because you don't want a mixture of products. You want it to be pure, right? So when sometimes you would have to calculate the percent EE to report the purity of your sample. Now, it isn't always possible to obtain an optically pure sample from a reaction, so sometimes we need to introduce a step to purify one enantiomer over another. And this turns out not to be a trivial task because enantiomers share so much characteristics, they are actually very hard to purify from one another. Remember, a lot of times we use melting point or boiling point or even crystallization to purify our samples. We cannot do it in terms of enantiomers because they share those physical properties. But it turns out diastereomers are not identical in this regard. So we now introduce a trick called chiral resolving agents. The word resolving here means to separate mixture of compounds or to purify. Okay, so let's take here an example. Let's say we have a mixture of these two compounds and they are enantiomers of each other, so it's hard to separate them out. What we can do is react this with a chiral resolving agent called S-malic acid. So when we use a chiral molecule to react with our enantiomers, they will create a salt, and these salts are no longer enantiomers. Also, this product may look intimidating, but if you take a closer look at it, it's a simple acid-base reaction. Okay, so go ahead and prove to yourself that that is an S configuration and the bottom enantiomer is the R configuration. So in its product, that remains the same, right? But remember that the S-malic acid, we said at that chiral center was an S configuration, so that didn't change either. So you both have S there. So these are salts, okay? So in this salt, you have an S versus an R and S. So based on the configuration of these two chiral points, what would you say the relationship of these two salts would be? It turns out these salts are diastereomers from each other. They will have distinguishing physical properties and therefore easily removed from one another. So that's a trick using enantiomers and diastereomers in order to achieve a task that would otherwise be quite difficult in the organic lab. Okay, so that rounds out our lecture in this chapter of stereoisomerism. We've learned what they are, how to designate them, and some of their practical applications.